Hello, everyone. Welcome to lecture 24 and the last lecture of the finite elements method. In this lecture, I would like to give you a quick overview of what we have done, and then we will have one simple example, which was indeed one of our final exams questions. So we will also do that. All right. So again, I'm sure you are now sick and tired of this roadmap by now. You have seen it so many times, but it's very important. I think this course, maybe for you, is not so difficult because you see this map so many times and you don't get lost. But my experience is that one of the main reasons that people find finite element method complex is that they do not see this big picture. So they do not see how the different pieces are connected together. So that's why I keep showing you this roadmap. But again, then you know the roadmap, and then you know how the finite element basically works. And it has this very interesting part, which we approximate the equation in the finite element method. This is the key to the finite element method compared to many other numerical aspects. So it's not only, so usually when we talk about numerical approximations, we know that we would approximate the solution. We know that we usually approximate the input to the solution. But the finite element method in particular, it has this additional thing that we actually change the equation itself. So the equation would be an approximate equation. And then again, if you think of a 1D finite element method, we have this basically detailed version of the roadmap. And the important thing is, again, that you start from the strong form, you get the weak form by just multiplication by test function, integration, and then you do this piecewise integration, which later in a two-dimensional form, in a two-dimensional FEM, this piecewise integration, it would basically translate to that discretization, right? So here, if it is just an integral, you would say integral from 0 to a to b, and so on. But this is exactly what we call discretization later. And then you do approximations using shape functions, and then eventually you integrate using Gauss quadrature. This gives you the stiffness of each element. The only thing you need to do is to assemble the elements, and then the assembly process alone, we have learned it before. So again, in a mathematical sense, this would be your strong form, and these are basically the key steps of the derivations that we have. We come to our stiffness as a function of x. So in principle, when you are here, if you use something like Maple or Mathematica, you can, or any symbolic mathematics tools, you can integrate this k already. But since we want to do it numerically, even after we have this one, we need to bring it to the natural space and then integrate it numerically. This is the key important, and then that's basically how it works. So we come to two-dimensional finite element method in the same sense. Now, the starting point, previously, it was basically our governing equation. It was something like u double prime is 0 in 1D. Now, we don't have exactly that. Our governing equations for a mechanical problem or for a thermal problem would be related to more advanced mathematical operators. And in this case, that would be the divergence operator. So we would have something like this, and this is basically the divergence of the stress plus body forces is 0, for instance. Okay, so this is your operator. And then it doesn't matter if it's a mechanical problem, it's divergence of stress. If it's a thermal problem, it's the divergence of the heat flux. Okay, so now that we have the strong form, we want to also learn about the shape functions. For the shape functions, I mentioned there are many different elements. The 5 most important or most basic elements here we covered. So we covered 3 quadrilateral elements and 2 triangular elements. And also we talked about their integration rules. So if you have a bilinear quadrilateral element, these are the shape functions. We learned together exactly how to write these shape functions, and we showed how these surfaces look like. We did the same thing for Lagrange biquadratic, for serendipity biquadratic, for linear strain triangle, and eventually for quadratic triangle. Also, we talked about the Gauss quadrature formula. It's not really super complicated. Previously in 1D, when you had a Gauss quadrature integration, instead of two integrals, you had one integrals in 1D. So now you have a double integral because you have integral over your area. And then instead of this, we usually call this thing dAc, by the way. Okay, so this would be some sort of integral over your natural space. So it would be something like that. And that integral, you can transfer it to a summation over the Gauss points. The important thing is that if you have a triangular element, there is this 1, 2 as a coefficient. Obviously, you can imagine it's just a coefficient, and then maybe in some books you can see that that coefficient is multiplied by the weight factors so that you do not have to write it. So there are two ways of writing this. This is a more common way to have actually the factor here and define the weight factors like this. But if you don't see a factor here, then pay attention. Possibly you can trace that in your weight factors. Okay, and then we have the same thing for the quadrilateral integration or integration of the quadrilateral elements. And also we have the Gauss points for that. Okay, again, this roadmap, and possibly the last time that you see this roadmap. Now you know how to do this approximate form. So basically we learned how to do this part. We also know how to do the numerical integration. We know the divergence of stress is your strong form. The only thing we don't know is what is the weak form. Okay, so the last thing you need to do is to basically connect the strong form to the weak form, and the process is exactly the same process as we did before. So you start with your strong form, which is that divergence of stress. You multiply it by shape functions, you integrate over the domain, and you do all those steps, and then you end up with this stiffness structure again. And then you can imagine if you have something like a triangular element, this would be a stiffness that is 3 by 3, but then each of these boxes, they are a 2 by 2 matrix, so it's indeed a 6 by 6 stiffness. So 3 by 3 means 3 nodes and 3 nodes. Okay, so the superscripts, as always, the superscript, if you remember from the beginning of the lecture, we said the superscripts are nodes and subscripts are directions. So direction 1 would be X direction. In this case, direction 2 would be Y direction. You can play the same game for a bilinear quadrilateral element. In this case, you have 4 nodes. So your stiffness would be 4 by 4, and then each of those stiffness blocks would be a 2 by 2 again, which is giving you an 8 by 8 matrix. All right, so if you think of these stiffnesses, again, for each of the elements that we discussed, for each of those 5 elements, we know exactly their dimensions, and we know how to calculate each of those components. Now we are back on that place where I said this is a function of X. Okay, so if you are doing it on a piece of paper, if you have a mathematical tool, a symbolic mathematical tool, you may just calculate this already. But usually that's time consuming, and what you want to do is to bring it again to the natural space so that you can also do the integration using the Gauss quadrature. So in this case, there are 3 things that we need to elaborate on. One is the constitutive tensor itself. So this is just the definition, by the way. It has nothing to do with the space that you integrate on. So this we need to address, and then we need to change the coordinates from the physical space to the natural space, and eventually you need to integrate using Gauss quadrature. And the constitutive tensor for plane strain is defined like this. So this is a two-dimensional plane strain. And then if you look at each components of that, it's going to look like that. So in the previous lecture, I think I had a typo here. There were also these news here that you can imagine why I basically copy pasted things. But there are no Poisson ratios there. So this should be the corrected version. In any case, it's not that important. This is the, let's say, the form, and you can calculate each of these as we had done together. All right. So now that we have that, we need to take care of these derivatives with respect to x, which is the physical coordinate. And in order to do that, you use the famous chain rule. So you would say derivative with respect to x is derivative with respect to c, derivative of c with respect to x, and then derivative with respect to eta, derivative of eta with respect to x. And if you play that game, then each of these brackets, each of these derivatives with respect to x can be written in terms of derivatives with respect to c, but then you would have this map basically between the coordinates or between the derivatives, and that would be J inverse transpose, where J is your Jacobian matrix. Now, again, the Jacobian matrix itself, by definition, is exactly the same thing as we had in 1D. It's simply the derivative of the physical space or derivative of x with respect to c. Okay, so we had this also in 1D, but obviously in 1D it was a scalar, and here it's not. Then you can calculate each of those components, and then you can write J, or rather J transpose, like this, very nicely in terms of the derivatives of the shape functions in the natural coordinate system and the coordinates of the nodes. So this is very nice. Or you can just do the transpose version of this and write the J itself, which now you would have the coordinates, let's say, on the left-hand side, and then you have this these derivatives on the right-hand side. So this is everything that you need. Okay, so based on that, I just want to summarize everything, and then we will show you the example. Okay, summarizing everything, what we have learned so far is that KijAC, which is the direction A of node I, so that's the force part, that with respect to the direction C of node J, that would be the displacement part, so that's the displacement, that's the force part. That would be your stiffness, and that stiffness is calculated using these summations over the Gauss points. Okay, now you see the two formulas are basically identical, except that this one half that you have because your element is triangular. Now, in this format, again, E is basically this. This is the definition we had for the constitutive tensor, and you can write those components individually. For your exam, you will be allowed to have a cheat sheet. So I suggest you actually write this to save time for yourself. You don't want to keep calculating it. So it would be nice to have it on the side. But then basically this slide is the summary of pretty much everything we did. Okay, so this is an important slide for you. And then again, if you want to have a more detailed version, you would have this one, but now they are very small. All right, the last thing that we did was to have this determinant of J all of a sudden as the mapping between the area elements. So basically what we claim here is that if you have a mapping between the two coordinates, a linear map, J, the determinant of that is the ratio of the area elements between the two coordinates, which makes sense if you think of this as the cross product of two vectors on the two coordinates. So you can basically prove that easily. But also we did some examples in the previous lecture to show how that works. Okay, so you have now everything. You have the stiffness, you know exactly why the determinant J is here. You have the constitutive tensor. You have this J, or how you need to construct it. And then you know the stiffness, for instance, for a triangular element. This is an example, by the way. For a triangular element, the stiffness is again 3 by 3 blocks, and then that gives you a 6 by 6 matrix. Now, for this particular example, you can calculate the stiffness, and that's what we do for a given set of coordinates. So if the physical coordinates are these, so basically we have that triangle which we just had in the previous picture, and then this would be node 1, this is node 2, and this is node 3. If you think of the stiffness of this triangle, this is what you get. Again, this is something that you need to actually calculate yourself, but this is a good example for you to test your calculations. All right, so you can do that. And then if you have particular material parameters, obviously for E and nu, you can replace those in these components and calculate the individual components of the stiffness. Now pay attention here, I'm using one Gauss point. This is not a big problem because we know it's a constant strain triangle. So inside this integral, we have everything as constant. Well, in the integral version, we know everything is just constant. So basically, when you want to use the summation, one Gauss point is enough. Okay, so one Gauss point is sufficient, whether nu is 0 or nu is 0.5. It doesn't matter. Now, if you play the same game for a bilinear quadrilateral element, so what I want to do now is to calculate the stiffness for this bilinear quadrilateral element, which would be 8 by 8. And by the way, the stiffness is always symmetric and is determinant to 0. So this is a good test for you to check if your calculation is correct. So if you do this using one Gauss point, you will get this. This is using one Gauss point, and these are, again, the coordinates of that stiffness matrix. Now I'm going to insert particular material parameters here. So assume E is 10 and nu is 0, for instance. Now, if you look at your stiffness, you get this using one Gauss point. If I increase the number of Gauss points to 4, if you pay attention to these, for instance, look at this block. It's 3.75, 1.25. You see that something changed. So these two didn't change, but these two changed, meaning that these two, they were not calculated accurately enough using one Gauss point. They need more Gauss points to read the information. Okay, so then you could ask, okay, maybe we need even more than 4 Gauss points. So we then test this with 9, but you can see if it is 9 Gauss points, nothing really changes. You may think something is changing because, you know, numerically, some of these zeros, they appear to be -0. So if I switch between the slides, you see something is changing, but actually it's not changing. It's just the 0. But the code, for some reason, it gives you -0. Okay, so we know that 4 Gauss points would be sufficient in this case. And then again, if you have a different Poisson ratio, you observe the same thing, basically. If you now look at this part, you can see that, again, increasing the number of Gauss points to 4 will change that, but increasing it to 9 doesn't change anything. All right, so that was everything. That's, let's say, a summary of everything we have done. Now, this is a nice example we want to look together at. And this was, again, the final exam, not the last year, the year before that. So you may want to expect something like this. But also I need to add that 2 years ago, we had also a midterm for the exam. You did not have a midterm. So in this particular example, we do not see truss elements because we asked everything about truss elements in the midterm. Since you did not have a midterm in your exam, you may also see or observe truss elements. So don't be surprised if you see truss elements and 2D elements. So instead of reading the example, you can look at the, let's say, the description. You can read it later in the PDF file or in the video, but I try to explain it on the picture itself. This is basically the structure. You have two elements, element 1, element 2. Element 1 is a bilinear quadrilateral element. Element 2 is a triangular element, constant strain triangle, so 3-noded element up here, 4-noded down here. The material parameters for each of these elements are given, and also the boundary conditions are given. So this is completely fixed here. You should pay attention to the, let's say, the constraint types. So if you look at these are basically fixed, but then these are rollers. Okay, so you should pay attention to the degrees of freedom that are constrained, because that will help you significantly to reduce your system, obviously. All right, so basically these 2 points are completely fixed. These two, they can move only up and down. This one can move in both directions, so it's completely free. All right, so you have that. So basically you would be looking at a 4 degree of freedom system, right? So you have 1 degree, 2 degree, and then 2 more degrees here. These are 4 degrees of freedom. Now, the important thing in this example and in all the examples that I give you for the exam is that I give you a specific numbering of the nodes and degrees of freedom. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the degrees, but they are not the degrees of freedom. The degrees of freedom later they come because of the constraints, but these are the degrees that you need to start with. Okay, I want you to write your stiffness exactly with respect to this, because if you don't do it, it's almost impossible for me to check it. There would be so many different variations. So you must pay attention to the particular numbering of the degrees and node numbering. But this is what it is. So you have node 1, 2, 3, 4 basically for the square element with the degrees 1, 2, 3, 4, 5, 6, 7, 8. And then for the triangle, the nodes would be 4, 3, 5. The degrees would be 7, 8, 5, 6, 9, 10. Okay, so that would be the order of the 6 degrees for the triangle. So here, if you want to think of that order, this would be 7, 8, 5, 6, 9, 10, which is 6. So you know your stiffness for the triangle is going to be 6 by 6. And you are asked to calculate that. But we want that exactly using this ordering of the degrees. And you would calculate that using 1 Gauss point. Then for the quadrilateral, this would be 1, 2, 3, 4, 5, 6, 7, 8. So it's now 8 of them. And then this would come to your 8 by 8 stiffness, which you also calculate using 1 Gauss point. So this is the first part of the task. You calculate the stiffness for this, you calculate the stiffness for this. Now, the next part is to assemble the reduced stiffness for the entire system. Now, in order to do that, you need to pay attention to the supports, and then you can see that you have these 2 fixed supports, so that means these degrees, they completely vanish, and then degrees 5 and 7 also vanish. So you would end up with degrees 6, 8, 9, and 10 as your remaining degrees in your reduced system. So your reduced system would be a 4 by 4 system with the degrees being 6, 8, 9, and 10. Now that you have that reduced system, I just ask you to calculate the displacement of node 5 in the x and y direction, so u5x and u5y, for these 3 combinations. So the first combination basically tells you have a force in the horizontal direction. That's it. So there is no vertical force. The second one tells you that you have a force in the vertical direction. The third combination tells you that you have a force which is having two components, one horizontal and one vertical components that are also equal. Okay, so you may actually have a good feeling that this case 3, is a summation of the two cases. So in fact, you do not have to solve it. If you solve the two previous ones, you can just add the results and you would have this. So let's see how that works. Again, the first thing is that you need to calculate the 8 by 8 stiffness for the element. And as I mentioned, this would be your numbering of the degrees. So again, this is 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y, which in this case would be degrees 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and then you calculate this stiffness using exactly what we learned together. Okay, so you know how to calculate this. I don't have to go one by one. By the way, when you do this calculation, I suggest you also use your own finite element code that you had written. It's a good test to see if this is correct or if your code is correct. Again, pay attention that the components on the main diagonal, they are all positive. It is also symmetric, and we do not see the determinant, but if you calculated the determinant would also be 0. Okay, so you can calculate the stiffness of the square element. Then we do the same thing. Now we calculate the stiffness of the triangular element. Now you see the degrees are basically based on these. So this would be node 4 in x direction, 4 in y direction, 5 in x direction, 5 in y direction, and 3 in x direction and 3 in y direction. So if you look at the way that these are basically sorted, node 4 would be, how can I, yeah, let's go. So node 4 is this one, 5 is this, and 3 is this. Okay, so if you just look at these, basically you can write this in terms of those numbers, like, I don't know, 4x and 4y, these are 7 and 8. And then you had 9 and 10 and 5 and 6. Okay, so let's say this is 7, 8, 9, 10, 5, 6. These are in the global system, by the way. Okay. So you should not pay attention to these anymore. These are the local ones, which we used only here. But those numbers that they go up to 10, those are the important ones. Okay. Usually for triangular elements, I suggest you start from this corner node and you go counterclockwise. In this example, we didn't do that exactly, but this shouldn't change anything. All right, so if you assemble the two elements, now you would have this one, and then these are those global numbers that we talked about. Which, by the way, I have never asked you to calculate this. This is just for fun. The question does not ask you to assemble the global stiffness, and that would be a little unfair. That's too much work. Okay, that's a very large system. So you do each of those systems. The question actually asks you to calculate the reduced stiffness matrix. So what you want to do is to find the components that are related to the reduced stiffness matrix. If you remember those degrees, the degrees for the reduced stiffness matrix, they were 6, 8, 9, and 10. So we are interested in, let's say, 6, 8, 9, and 10, if you think about it this way. And then, again, that would be 10, 9, 8, and 6. Okay, so these are the components that we are interested in. Okay, so this is that 4x4 matrix, the reduced one. Okay, so the reduced one would be something which would have this, which would have this block, and then this would have this one, and this one, this one. All right, so if you, I don't know if you can sort of memorize this or just take a snapshot in your head. If you just look at these red numbers, these are exactly what you have here. So this is your reduced stiffness now. Okay, and the degrees again are basically the degree that we talked about. All right, so you put that stiffness and then you multiply them by their corresponding displacements. So Ku equals F. And then again, if you remember, this is 4y, 3y, 5x, 5y. But the orders that you have here is, yeah, I don't like this. Okay, this is basically 8. This is 6. This is 9. This is 10. It's not too important because in particular this system is symmetric and it doesn't change much. But I think I told you at the beginning that you should have started with a different order. It doesn't matter in this case because I am let's say we explicitly write the node numbers and directions. Okay, so you shouldn't have a problem with this. All right, now you would have that Ku equals F system. Now on node 4 and node 3, what are the forces in the corresponding direction? In the y direction in this case, it's 0, right? So node 3 and node 4, they are free in the y direction. So that means you would have zero here. For node 5, in x and y directions, you would have fx and fy. All right. So this is basically your system. Now you want to solve this. You have 4 equations, 4 unknowns in principle. It looks harder than it is, so it's not a very difficult 4 equations, 4 unknowns. If you pay attention to the coefficient, they can easily simplify together. But also you can use your calculators for this anyway. But in particular, if you set these numbers, so for instance, in the first case, you know fx is 1 and fy is 0. So if you set that, then you can easily solve this system. So for this particular case, if fx is 1, fy is 0, you see you get u4 and u3 in the y direction. You get opposite values. So u4 is positive, u3 is negative. u5 in the x direction is positive and in the y direction is 0. So let's see what that means. That basically means if I apply a force like this, what happens is that this node is coming up, this node is going down, which kind of makes sense to you, right? And then this thing moves like this. Okay? So your structure would look like that. Does that make sense? So U5 moves in the horizontal direction, a little bit to the right. Remember the direction, let's say the plus direction for x and y. Plus is towards right and y plus is upwards. So U4 was plus, U3 was minus, but the same value as U4. So you would get this. U5 was plus, so it was something like that. And then basically it gives you this triangle. And the rest of the nodes are easy because they are fixed. And then also these nodes 3 and 4, they do not move in the x direction. Okay, so this kind of makes perfect sense. Now, if you have the other case where fx is 0 and fy is 1, what happens? u4 and u3 in the y direction, they are equal. u5 is 0, and then u5y is 2 times those, basically. Okay? So this tells you that these two nodes, they move up a little, both of them. So this would be that. And then you would have this triangle, basically. So node 5 also moves up. All right. Do you have any questions? Okay. Eventually, if you have fx equals 1, f1 equals 1, you can clearly see that the solution to this case is the summation of the two. So if you add these two, imagine, so remember, we have a linear system, right? So if you apply these two forces separately, it basically gives you the same thing as you would apply them both together. We call this the principle of superposition in ME 231, right? So you have exactly this superposition. So basically, if you have forgotten that you had superposition, you solve this. If you don't, then you can use superposition. You don't really have to solve this. You will just add these two together, you get this. You will add these two together, you get this. Add these two together, you get this. And then add these two, and you get this. Okay, this is basically principle of superposition. Okay, so this was the example. This was basically a question for a final exam. Your exam should not be particularly more difficult or easier than this. I like your exam more. I don't tell you more about that, but I like your exam more because I think you will actually, after your exam, you will learn something that maybe until now you don't know. So it has some additional learning values for you too. All right, do you have any questions, comments? If not, then I will thank you very, very much for this fairly unusual semester together. I think we all know it was not ideal to have this online course,